So starting with the condition of first order phase transition, what we can obtain is the Clausius-Clapeyron equation. We had already obtained Clausius-Clapeyron equation. Now starting with the using the condition for first order phase transition, again we can obtain the Clausius-Clapeyron equation. So here we will start with the condition that the Gibbs free energy for both the phases are same for first order during first order phase transition, and we also know that Gibbs free energy is a function of temperature and pressure. So what is this graph? Here what we are showing that suppose this side is phase 1 and this side is phase 2. So this line shows the phase transition from phase 1 and phase 2 at different pressures and temperature. So at pressure so this point indicates that the substance changes from phase 1 to phase 2 at constant pressure P and constant temperature T, because we already know during first order phase transition pressure and temperature remain constant along with the Gibbs free energy. So this point indicates that at temperature pressure P and temperature at pressure P and temperature T, the substance changes from phase 1 to phase 2, and during that transition in phase 1 the Gibbs free energy is G1, and in phase 2 Gibbs free energy, specific Gibbs free energy is G2. So what we can write at point A where the pressure is P and temperature T, specific Gibbs free energy of phase 1 G1 is equal to specific Gibbs free energy of phase 2 G2. Now then the transition can happen at a different pressure and different temperature. So here this point B indicates where the transition is happening for the same substance, and the substance is converting from phase 1 to phase 2 at a different pressure P plus delta P and at a different temperature T plus delta T. So what we can write at point B, which is at pressure P plus delta P and temperature T plus delta P, again the Gibbs free energy during this transition, the Gibbs free energy will have some different value, because we know Gibbs free energy is a function of temperature in P. As pressure and temperature are now different, so at this point P the specific Gibbs free energy its value will also be different. So for phase 1 this value is G1 plus DG1, and for phase 2 this value is G2 plus DG2. But as this is the first order phase transition, during this transition these two values will be equal. So what we are writing at B, again the phase transition is happening, suppose at different temperature P plus delta P, at different pressure P plus delta P and a different temperature T plus delta T. Then the specific Gibbs free energy of phase 1, which is now G1 plus DG1, is equal to specific Gibbs free energy of phase 2, which is now G2 plus DG2. So now what we can do? We have already seen that G1 is equals to G2, so we can cancel G1 and G2. So what is left? DG1 equals to DG2. Now we know G is a function of T and P. So we can write dG as del G del T constant P dt plus del G del P constant T dP. So from dG1 equals to dG2, what we can write using this relation, we can write that instead of dG1 we are writing del G1 del T constant P dt plus del G1 del P constant T dP. Similarly we can write same thing for dG2 in terms of partial derivatives. So now we have already seen that this del G1 del T is equal to minus S1. This is the relation we had learned this in free energies, and del G1 del P is equals to V, and since this is dG1 the specific volume, it will be V1. Similarly we know del G del T constant P is S, so but it is for del G2 phase 2, so it will be minus S2, and del G2 del P constant T will be V2. Now what we are writing in next step, we are taking all these dP terms together, so we have V1 minus V2 into dP equals to S1 minus S2 into dt. So dp by dt will be S1 minus S2 by V1 minus V2 equals to S2 minus S1 equals to V2 minus V1. So this clearly shows that S2 is not equals to S1 and V2 is not equals to V1. Means during first order phase transition, when the substance goes from phase 1 to phase 2, there is a change in entropy. So we have different value S2 minus S1, and similarly the volume changes. Okay, there is an abrupt finite change in the volume. So what we have? We have V2 minus V1, and V1 is not equals to V2. If both the quantities were equal, then this dp dt will not have any meaning. It will be 0 by 0. But this is not the case. So now we know, so you see this S is a small s, right? Specific, indicating specific per unit mass. So we know S2 minus S1 equals to ml by T. So this is ml. It is the heat transferred during phase transition. We know that change in entropy is Q by T. And what is Q? Q is the heat transfer during phase transition, which is m into L. M is the mass of the substance and L is the latent heat for that specific type of phase transition. Okay. So now what we are doing, next step, we are bringing m in the denominator. So S2 by m minus S1 by m equals to L by T. So S2 by m is the entropy of phase 2 per unit mass, which is specific entropy S2 minus specific entropy S1 equals to L by T. So if we replace S2 minus S1 with L by T, we get this relation dp by dt is equals to L by T V2 minus V1. So this is the Clausius-Clapeyron equation. So for different type of phase transition, we have this relation dp by dt fusion is equal to the corresponding latent heat of fusion divided by T V2 minus V1. For vaporization, we have this relation, and for sublimation we have L. Sublimation means latent heat required for sublimation divided by T V2 minus V1.